Okay, hello and welcome everyone to the second of the Fault2SHA Learning Series. We were delighted to have Lucilla Benedetti last time, and today I'm really happy to welcome Francesca Cinti. I know she is well known to quite a few of you. For those of you who don't know her, she has over 60 peer-reviewed publications with over 1,800 citations to do with earthquake hazard, paleoseismology, and topics relating to these. So she certainly is a great person that we're very excited to hear from today. She's going to be talking about paleoseismology in hazard modeling. As with all of our learning series, the idea is really to help everybody working on related topics actually understand what we're all doing, not just at the level where we're getting presentations in conferences, but actually sort of stepping back a level and sort of going back to slightly easier levels so we can all understand, and we hope that that will encourage future collaboration. So with that in mind, while Francesca is talking, if there is anything that's unclear, if there's anything you'd like her to explain a bit more about, please do interrupt, do ask questions, and she'll welcome them as we go along, and hopefully there'll be a little bit of time at the end as well. As we are all on Zoom, we ask that you keep your microphones muted throughout the talk, but if you do want to ask a question, just unmute your microphone and fire away. So with that, once again, thank you so much to Francesca Cinti for joining us today, and I hand over to you.
So thanks to you, Joanna, and hello to everybody. So first of all, thanks for inviting me to this learning series. I've been talking about palaeoseismology and palaeoseismological data, and to this audience, and many of you are not familiar with this discipline, but you are involved in a complementary field. So the purpose is to improve our capability in incorporating this kind of data into seismic hazard models, and also to stimulate the collaboration between data providers and modelers. So keeping in mind this line, I will my lecture will be divided in three sections. One is the first section where we will have an overview of palaeoseismology, then data output section, and then hazard, where I will make some reflection on data variability under a palaeoseismic perspective, and also I will present you an example of trenching-based rupture scenarios. So first of all, what is palaeoseismology? Is the study of the occurrence of the location and size of ancient earthquakes, and try to contribute to answer to the following question: how often do large earthquakes occur? When did the earthquakes happen? How large were these earthquakes? And how fast the fault is moving? So I think that we all agree that just having half of an answer to this question, so we are already making large advances in prediction. So, but how does it? The palaeoseismology use the recognition of the geological and geomorphological expression of the earthquakes, as, for example, in other words, the analysis of earthquake preserved of the earthquake effects preserved on the natural environment. So why it's important to do this? Because the more information we have about the past timeline of earthquakes, and the more we'll be informed about what is going to happen in the future, and also to improve our ability to plan action for mitigating of both the shocks, both in the immediate of the earthquake, but also years after the earthquakes occur. So there are several fields of data that are important to study the deformation in time that we can use. And first, let's say seismological data that are very accurate. We are talking about, we know that seismological data will have a threshold of detection of minimum of really low magnitude, lower than 1, and also very precise location of the hypocentral, but these are too short if compared to the life of a fault. So, and then we have historical data that are quite detailed, and the threshold of magnitude is magnitude 4, and the minimum threshold is magnitude 4 and larger. But these are not completely reliable or complete. It depends on where the earthquakes occur, and even the historical period. And also there is no fault assigned to this earthquake, but it's very important, they provide precise age of the earthquake. But they could be still not long enough, even if compared to the longer recurrence of large earthquakes. So till a few decades ago, but now things are changing, seismic hazard assessment was based solely on these two type of data, and they were excluding the geological records. So this could create problems in forecasting, in assessing the probability of future earthquakes. So palaeoseismology, which has a minimum threshold of magnitude 5 to 6, supply the short time span and extend the earthquakes record into the past, and also assign earthquakes to fault and define the activity of the faults. So it helps to have a long-term vision of the recurrence and pattern of seismicity, indeed depict multiple seismic cycles. But still, the palaeoseismic record are needed, but needed to be detailed and time constrained. When you read papers now, authors try to cross-correlate the complementary data and information to fill gaps and to have better constraint of the trend of the events history. So, but let's see which are the palaeoseismic evidence that are indicators of earthquake recognition. When an earthquake equal and larger than 5.5, about 5.5 occur, it can create instantaneous and permanent deformation on the surface. And this can be very close, can occur very close to the source, or even kilometers, tens of kilometers apart. So the deformation, when occurred, produce perturbation on the topography, and so a new process of erosion and accumulation are triggered. And so if we repeat these cycles in time, so surface rupture that are accumulated, we have a shape, we have the earth that is shaped, new landforms and structures. And these are the geological imprint of earthquakes. Let's just think about the growing of ridges, and then changes in river flow, or new lakes that forms. And so a statement is that palaeoseismologists can study earthquakes producing recognizable deformation in the form of deformed stratigraphic units, displayed landforms, or earthquake-induced sedimentation. So there is a nomenclature that is used to distinguish the palaeoseismic evidence, and based on the cause or the distance from the earthquake fault. And so we have primary evidence that are produced by the ecoseismic slip on the fault plane. And among these are fault scarps, both fossils or fresh, and are pressure ridge, or linear valleys, shutter ridge, or deflection of stream. These are, let's say, the expression of the fault at the fault of the fault line. And these are called on fault. But also we have the surface, but we have off fault evidence, which are far apart from the source, and are those surfaces that have been tilted, uplifted, or down dropped, or torn apart. Figures shows just some of these features. And the minimum magnitude threshold, I want to say that is really decreasing because of also of the advances in the remote sensing surveys. So let's just think about the 4.9 earthquake in France in 2019. So even if the surface rupture is really subtle, we have the help of these remote images for sure. But what to keep in mind about the primary evidence is that they reflect the movement along the plane at depth. So, and the type and size is related to kinematic, the dimension and the geometry of the rupture plane, and also the magnitude of the earthquake. And they records earthquakes from single fault. Secondary evidence instead, first of all, we need to exclude non-seismic process origin. And then if excluded, they are produced by the shaking during the earthquake. And we have disturbed trees, damaged skeletons, liquefaction, rock faults, landslides. And this can be occur both on fault and off fault. But relative to respect to the primary evidence, these effects can include evidence of earthquakes from various faults, from various locations and distances. So it's really difficult to associate this to the causative fault. But this is not negative. I'm really a fan of secondary evidence because these are essential where fault is not accessible. Let's just think fault under the water or a fault that is blind, or actually an unmapped fault. So, and also this evidence provides data for regional seismic hazard evaluation, provides information on earthquake potential shaking intensity. The Palaeoseismic investigation generally progress from a regional to a local and then site scale. I will show you some talk about on-fault investigation. So this means that we are looking at the deformation at the local and site scale. And the approaches that I will talk about are two for palaeoseismic reconstruction: quantitative geomorphology and trench excavation. And I think that Lucilla already presented to you another approach, which is that one with the cosmogenic nuclide for on fault scarp, which is always a non-fault approach. So quantitative geomorphology basis on geological mapping of quaternary deformed surfaces and deposits in the zone of deformation, and aim to identify deformed geomorphic surfaces. So let's say just like a fan or marine terraces or river course, and to define style and rate of deformation across landforms of different ages to indicate where the fault traces are a result of single or multiple events. But under a modeling context, let's say, so the quantitative geomorphology maps the fault and maps structural complexity of the faults, defining rates of fault activity. And so these are elements among the elements that control the rupture extent, and so really critical to characterize the future rupture. And for this reason, segmentation models should be based on behavioral differences and kinematic variables that are also structured by through this approach. Of course, increasing technological capabilities really sharpened our view with our resolution topographic data, and the LiDAR-based dam is really effective in the near fault, particularly in areas where we have a very dense vegetation or rugged topography. So it helps to visualize also hidden faults, let's say. So trenching is the well-established approach of subsurface investigation of faults, and aims to identify and date the stratigraphic sequence that contain information on the faulting history, to quantify the dislocation, and to regulate palaeosurface ruptures. So the first critical step for trenching is the site selection. It's very critical, and on this depends the success or also the failure of our investigation. We should base before to dig a trench. We should have a really clear idea of where the fault line is, but also particular we have. We should recognize the cumulative deformed features first. And then we have other points to look at. For example, it's better to concentrate on a single narrow fault strand, or just to look for local fault zone depressions that are filled with fine grain or organic sediments. So we should figure out before in advance which kind of stratigraphy we are going to expose. And of course, geophysical methods help really a lot to locate the trench, both georadar or electrical resistivity, and also they extend the fault trace at greater depth. So which kind of data palaeoseismological measure? Deformation cumulated in a specific interval of time, mostly with quantitative geomorphology, and then also age and size of the deformation of single earthquakes, mostly by trenching. Site-specific measurements measures most recent event, timing of multiple ruptures, surface displacement. And based on this measurement, we can estimate parameters that describe the seismic behavior of a fault, which are slip rate, slip event, recurrence time, elapsed time. And all these, just looking also at this nice diagram from Morel et al., are the input data that goes into feeding the models that are the elements of the probabilistic seismic hazard analysis. So a geological contribution to PSHA. So let's see very simply, in a simple way, how we estimate these parameters from the geological signature. So slip rate is a deformation accumulated in a specific interval of time at different spatial and temporal scale. And for example, on strike slip is calculated from measurements of the offset of any landforms that is cut by the fault, and that is datable. Here is an example where the surface displays the landforms are moraines. And I want just to let you notice that we provide, of course, uncertainty errors of our measurements, and also both of the distance between related to the offset of the piercing point, but also related to the dating of the landforms. So based on Fault2SHA morphology, it's difficult to discriminate on the number of past displacement events. So deformation from multiple individual paleoearthquakes can be recognized also from the analysis of scarp profiles. Again, very briefly, this is I'm talking about scarp in soft sediment. And this is a compound fault scarp, or what we call compound fault scarps. That is a fault scarp that is produced by more than one rupture event and is characterized by multiple breaks in slope, each originated in a separate rupture event. So finally, the profile, it appears like segmented in different segments with different dipping. And the vertical one is the fresh portion of the scarp, and then we have a retreated portion that is referred to the previous event. Even in this case, we have the high resolution DEM are really helpful because we can have, again, through their analysis, we can depict punctual changes of the slope, and so have analysis of the distribution of the slope also along the strike of the fault. Some cases, this is not the scarp. I want to just to focus on the different dipping of the slope. There is 1981 scarp, the fresh and vertical section, and then the scarp face of penultimate event that is retreated, and then a natural surface slope angle. Just notice that there is always colluvium at the base. There is from the erosion of the scarp. So slip rate in trenches is, we use the estimation of, again, estimation of amount of deformation we need and the age of the deformed sediments. But this is a very simple log, which is a graphic reconstruction of the wall. And very simple, but I will use this also for the other parameters. And there is an earthquake occurring at the surface, 1994, that offset the surface. And of course, when an earthquake occurs, we have surface rupture, all the deposits below are offset as well. So slip rate, we measure the total displacement recorded by the exposed sequence all across the fault zone, and we measure and also if we have the age of the deposits exposed, we can measure our slip rate. That is, in this case, the total displacement accumulated in the time span between the occurrence of the 1994 earthquake rupture and our age, which is in this case 700 CE. So I want to just tell you that the measurement of vertical separation is the project of surfaces and contacts to and across the fault zone. And what we provide in our papers is that the projection is our best estimate of the original depth of the deposits. But of course, we provide also variability. Slipper event is the amount of coseismic surface displacement produced by single event. And of course, we can estimate this parameter only if single events are recognized. And always the same log. What we observed is that the earthquake, that 1994 earthquake, and they produced 20 centimeter of offset at surface. And then looking at measuring the offset also of the layers below, we observe a discrete increase of the dislocation with the age of the deposits. So the slipper event, so it means the deposit experience past dislocation, and our slipper event is the amount of the increase. Where we observe this discrete increase, we can set the ground surface at the time, or event that is called event horizon, the ground surface at the time of the event occurrence. So how an earthquake looks like in the trench, this is, so the palaeoseismic features, this is one of these, I mean, a discrete increase of the dislocation with the age of the deposits, but I will show you some others. For example, this is an example of a trench in L'Aquila in 2009. We have clearly observed that the sequence is displaced and sharply drops down the same direction. We observe an increasing of slip with depth, even in this case, and set our event horizons, where we observe the increase. The event's age is bracketed by dating the youngest datable stratum deformed by the event and the oldest that overlie the horizon. And of course, the more distant are the sampled layers, and the larger will be the uncertainty on the age of the event. Okay, other photos. Here I want to remark that even small offset, it was in this case, we were looking at a throw of about less than 10 centimeter. And we can have a really nice view, I mean, of the fault depth, and also we can also reconstruct the past history. But so the remark is that the detection of few centimeters of displacement is a challenge, because these are associated to events that are around 6, and these are more frequent than the larger events, and they can be damaging. And of course, we also see, unfortunately, they can also produce casualties. Modern technologies are applied also in palaeoseismology, and so trenches, the trench wall can be visualized in 3D with structure from motion photogrammetry, from ground-based imagery. And also we can apply the TLS technique to visualize some contrast in the structures, and also in the both in the stratigraphy and structures. And both of these are resolutive for, let's say, unreachable outcrops or speditive survey, or also to fix a log before collapsing. Another palaeoseismic feature, actually, is a structural evidence inside the trench to set the event horizon, is the upward fault termination, which is most effective in identifying the most recent event, but not only. One case, so the fissure forms at the surface, at the ground surface with the event 2, and then the horizontal younger deposits are offset along the different trace with a successive event. Another case, in this case, we have that this deposit is faulted twice along 2 different fault traces. But life is not always so easy. We may have stratigraphy missing, just like in this case, our feature is that is the fault termination is completely cut, and so stratigraphy is missing. We will have a wide age interval for the event, and the age of the undeformed layer will set the maximum age, maximum boundary of our age interval. Now, another structural evidence are fissures. We need to take attention to the stratigraphic characteristic, both of the filling, open fissure, then overlying. And we need to see if the void space filled with parts of the overlying units and fissure and sheared, or filled by younger sediments. And this, of course, based on this, it will depend that we will have a different horizon. It will set a different level of the stratigraphy, and different is the age assigned. Colluvial wedge, we were looking also at the other picture that we had loose material exposed on the scarp face that falls to the base of the scarp and creates a wedge-shaped deposit of colluvium that overlie the pre-faulting surface. This feature can be found buried inside the trench, and so our event horizon is set at the base of this colluvial wedge and utilized to interpret the faulting history. And there are uncertainties related to dating, because in general, the lower part of the wedge, may be derived primarily from stratigraphic units on the crest of the scarp eroded during later scarp degradation. And so for dating, it should be better to date the soil below the colluvial wedge or immediately on top of the colluvial wedge. But most of the time, we also find some material to date inside the colluvial wedge, so we have to resolve the problem if the event is older, younger, or close to the colluvial wedge sample. This is a nice example of Borapic of colluvial wedge pilot in two different events. Okay, recurrence time, always the same log, very simple. Recurrence time is the average interval of time between earthquakes on the same fault. We had an earthquake in 1994, and we can make a direct calculation, of course, when it is possible to recognize and date individual earthquakes on the fault. And what we saw even before, we noticed increasing displacement. We set our event horizon where this occurred. So we have the recognition of two events prior to 1994. And so we have two inter-events in the time span in between 1994 and the age of the stratigraphy exposed. The last parameter, very important, is the elapsed time. It's the time elapsed since the most recent event on the fault, and can be estimated only by palaeoseismological investigation for faults that do not have historical earthquake associated with high recurrence interval. If the inter-event elapsed time approximate or is larger than the recurrence time, the fault may have accumulated sufficient deformation to be seismically released in the short term. And actually, in the Apennines, for example, we see that there are some faults, several faults that are ready to go, and we call them silent faults. And the North Shah fault is one of these that ruptured in 2016. So in summary, which are the direct measurements of palaeoseismology is the location of the trenches that have GPS measurement uncertainties, the dating of samples with associated errors from the lab, and offset and throw uncertainties by repeating measures. So fault data and fault parameters are represented by numbers, and errors are quantified, and modelers may include the measurements. So but there are sources of uncertainties in paleoearthquake dating, and all converge, of course, affect the event chronology. And to have an accurate event chronology is very important because it defines the mode of earthquake production. To earthquakes, Palo earthquakes, we cannot define a certain age to Palo earthquake. They are defined by time interval, and the width of the time interval is the Palo earthquake age uncertainty. So dating, radiocarbon dating method is a numerical method, so ages with stated errors, and dating accuracy is not the largest error. Errors may involve the stratigraphic, as we saw in the example, orthomorphic context of samples, reflecting uncertainty of relating the age of the dated sample to the age of the deposits, and arise for several causes. Sample quality, for example, is contaminated material, different ages in the same layer. I don't know which one to choose, and the upper layer younger than the lower. So I have a reversal in the stratigraphy. Event horizon not preserved, as we saw. So the event horizon is marked by unconformity. So we do not have we do not have solution, let's say, but we can reduce uncertainties, and with many actions that polysystemologists can apply. First of all, multiple palaeoseismic evidence. So to set the event horizon, use more than one evidence inside the trench. Multiple excavations, because trenches, one trench could, in case, not show us the full, the complete history. And also use different dating methods, which is very important. And then if stratigraphy is missing, we should estimate rate of deposition for constraint. But of course, I need to do this. I need to detail the age of the stratigraphic succession, and this means a lot of money. And another point is regarding the presentation of our data, that we should present the data uncertainties adequately, acknowledge the errors that are difficult to estimate. The fault displacement hazard will be the focus, the topics of the next lecture by Paolo Boncio, but I want just here to make some observation from a palaeoseismic perspective on this. Because palaeoseismic data provides the framework, let's say, for fault displacement hazard, recognizing, characterizing, and providing the accurate location of fault, and also estimate the expected movement. Concerning the fault recognition and characterization, there can be some issues, even if the expression of the fault is good. Indeed, palaeoseismic resolution may be lacking. Stratigraphy and rate of sedimentation do not allow to prove faults are not always active. So there's not much to do when this happens. So we need just move. And then also another issue is the variability of palaeoseismic data collected that are, of course, data collected at a specific point, and the variability is in time and along across the full width of surface faulting. And there's a lot to do with this. Variability of surface displacement at the point, that also means slipper event measure for successive event on a fault. I really appreciate the paper from Ecker et al. 2013, which is an attempt using a composite global data set of palaeoseismic data and explore the coefficient of variation values of surface ruptures. And so this is a figure that where I've shown they computed coefficient of variation values for the entire data set, and for subset of data, strike slip and dip slip, incorporating the certainty of the displacement estimates. So what they found is that the variability of surface displacement at a point on a fault is represented by values, CV values around 0.5. But I think that I found interesting to notice that the coefficient of variation of the entire data set is larger than that for reliable data. This means that lesser quality data increase the observed variability, although not significantly. And then another observation is that coefficient of variation of small displacement data sets is significantly higher, greater than that of larger displacement data sets. So this could be explained in two different things: greater measurement error for smaller displacement, or greater variability in the distribution of displacement for smaller ruptures. But so I found that the authors were good in finding the logic process for providing robust fault data to model. They made a compilation following specific criteria, revision of the papers and classification of the data in. They found consistency in the evaluation referring to a list of possible sources of uncertainty, and then they made a selection of lesser quality data to be removed. So there's a lot to do to explore this variability of surface displacement at the point, but we need to acquire more data for different magnitudes of the eruption and also at the multiple sites. So if modeled surface rupture is difficult, I think that the mapping of surface rupture can be even worse, both across and along the stride, because of the complexities increased with the earthquake magnitude. We can have very narrow deformation zone, but also we can space even kilometers far apart. So, and at surface, the slip is partitioned along a main rupture and subsidiary place, and we need to find a way to simplify for modelers. And the distance of distributed ruptures from the main fault ruptures and the width of the ruptured zone, slip distance function of distributed faulting are all issues in PFDHA, and I think Paolo will talk about this in March. But I want to fix few observations that major displacement occur across the main rupture, but small displacement in any case has to be included for the estimate of surface slip along the fault. This small rupture needs to be mitigated also by engineering. So how do we characterize secondary faults? How are they useful to reconstruct the seismic history on a fault? I have a first observation that comes from the NORCHA surface rupture. Here is the antithetic rupture that formed 3 kilometers facing apart from the main rupture. And what we can say that the antithetic, the antithetic fault did not move during the 6.0 almost 2 months before, but moved with the 6.5. So antithetic fault most probably moves always in conjunction with the main and only with large events. And then trenching record on this fault likely refer to large individual events. And this is, I think, that is really an opportunity to catch for trenching, because a slip from 2 successive earthquakes of different sides and clustered in time, just like we had at 6.0 after a few months 6.5, they cannot be distinguished in the palaeoseismic record, but they are interpreted as due to one slip event. Then investigation on secondary splay may be the key to avoid error in overestimate the magnitude in case of clusters. And the second observation is that always observing the surface rupture from NORCHA event, 5 subparallel splays fractured, and actually within a zone up to 3 kilometers wide. And so more than one trench is needed to address the slip history. If we just dig one trench, we will have really minimum values of in our estimates. And the third observation is that I do not any systematic investigation on the long-term expression of inferred secondary faults where minor displacement is expected. And actually it remains instead a lot of questions pending. Variability at the point of subsidiary synthetic antithetic splays. Are single displacement representative of long-term and future behavior? Is recurrence behavior on secondary faults well understood? And then are these subsidiary forever? So secondary fault characterization may be a challenge to implement, but we need a large amount of data to explore the variability and in geometric and displacement complexity. And anyway, all these questions arise also if we look at the palaeoseismic data along one of this secondary line that moved, that ruptured during the 2016. So the record before recorded, the data recorded before the event were pointing to 45 centimeter of minimum vertical offset. Slipper event, a fault length at surface 18 kilometer, and an expected magnitude of 6.5. So 13 years later in the future, actually, we had the 6.5 rupture, a 20 kilometer long surface rupture, but a few centimeters of throw exactly where the trench was dug. So in light of the 2016 palaeoseismic perspective, more than what this 45 centimeter represent cumulative throw, so more than one event very close in time, or we are looking at slip variability in time at the same single splay. So variability of earthwork recurrence, that means different distribution of the recurrence time on faults. We know that it can be very highly variable. There are many examples that identify this variability. The reasons are not very clearly stated yet, but we need a long series of accurate earthwork history, both in terms of ages and size of paleo earthworks on the fault. We need investigation at different location of the long term, and we need to reduce uncertainties on correlation among events. I will just show you the example of the L'Aquila event, but there are not because it's the most well constrained, but only because it belongs to me, and also because it's the first time that in the Apennines palaeoseismic records point to this kind of a variability. And actually merging the recurrence variability with the observation of the greater slip for older events, we obtain suggestion also for clustered smaller events separated by longer time intervals during which large events occur. And something similar we observed also during opening trenches across the North-SHA surface rupture. So, but let's arrive to the analysis of palaeoseismic data of the central Apennines we are currently conducting to, as an example of using this kind of data to simulate rupture scenario. So we apply a quantitative multi-step method based on sweep line algorithm, and so set an original approach to evaluate and integrate palaeoseismic data from multiple sites into an individual fault earthquake history. We produced, the products are paleo earthquake database, rupture scenario, different spatial scale at the scale of the fault and fault system, and define the regional characteristic of earthquake recurrence or rupture scenarios. And we have a double aim. First, to explore fault behavior, earthquake recurrence, and possible past regional clustering of earthquakes, but also we want to evaluate the potential of this 30 years palaeoseismic data for developing predictive models of earthquakes at scale of time and magnitude that affect the region, Central Apennines, which is one of the regions with the highest seismic potential in Italy. So on the map is shown with the yellow rectangles are shown the trench sites that are considered on 10 faults, selected faults. We selected 10 faults in this analysis. We are testing, but we are ready with other 6 faults and reaching a total of 80 trench sites to analyze. And but also in the development, we want also to include other past records from Unfault Investigation or also from other kind of Unfault Investigation. So building a paleo earthquake database is not so straightforward. We do not want to lose information, and reading papers, we noticed that resulting chronological sequence of paleo earthquakes has a different level of uncertainties and also accuracy that reflects the number of excavations, the data quality of the assumption used to narrow the age intervals for the event occurrence, and also the progress of palaeoseismological knowledge and techniques over time. And so we thought that we could make a kind of process to disaggregate data, so to separate in the different stages of elaboration of the authors to make the data set more homogeneous. So we started with 10 faults, 46 trenches, 15 scientific paper since 1996, actually to 2011. And so what we started with the systematic analysis and review of this paper. And so we could achieve the first target, that is to improve our capabilities in the palaeoseismic data analysis and raise awareness on their potential. So and then indeed we apply the model to different stages of the data review that are mainly related to the uncertainties of earthquake recognition and age estimates. And then also the process tend to ensure the replicability and reproducibility of the data. And so what we extract from the papers are PAL events recognition, time of occurrence, but we have also slipper event and slip rate, but the first two are those that we analyze in this first test. So the results of this process is 109 events in the last 28 kilo years, up to 7 earthquakes for individual trench. So this is the database structure. Actually, is the core. An example from one fault. This is the Vindolipezza fault, where we have 5 trenches. Each string is for a single trench, and are the record express the records of the different the history. What I want to what it's important to say is that that what we did is that surface faulting age intervals with different levels of review are represented in two categories reported in 2 columns. One is called the clear data columns, and the other is the further constrained column. Clear data column are age interval limited by the measured lab ages, absolute dating, objective datings. And these are data that we can say that are cleared from authors' expert judgment, let's say, or from some of potentially biased interpretation. So these are the intervals are the most conservative and widest. And then there is the column of further constraints age estimate, where estimates are supported by relative dating consideration, generic stratigraphic consideration, historical consideration, trench cross correlation, archaeological evaluation. And so these further elements provide suggestion to set a new maximum and minimum or minimum limits, also insert values that were previously undefined, and also identify preferred time period for the event occurred. These may include assumption and judgments that possibly suffer subjectivity. So we distinguish them, and also we want just to point to the coded criteria to separate the variables used by authors for setting ages in papers. Here, as an example, is a part of the interval preferred based on stratigraphic consideration. So we marked that. And then preferred age here, we didn't have the younger boundary set in the clear data. But then inserting the further constraint, we set the value previously undefined based on historic and archaeological consideration. The data set, the structure has also other parameters, for example, longitude and latitude of the single trench, new measures. And then also we point to the trench where dug on the antithetic, for example. The search of age correlation between events from different trenches is critical for decreasing incompleteness and uncertainty of palaeoseismic data. We apply this quantitative multi-step method. This is composed by three main steps. Step one, define a multiple trench integration, finding the possible intersection between events from each trench, and this is based on clear data. And then we introduce further constraint data to reduce the uncertainty, and in this way we built alternative rupture scenarios on individual faults. And then we have step two, where we search for chronological correlation among ruptures and adjacent faults. And this is critical to have because we may evaluate rupture dimension and even the magnitude expected. And step three, we identify possible rupture history for all the studied faults together. And so providing estimates of earthquake recurrence interval and earthquake rupture patterns for the whole region. So the first step, individual faults, the algorithm leads to different combination of palaeoseismic trench data for each fault, and we obtain a total of 28 scenarios from clear data. 6 out of 10 faults combination leads to a single possible chronological sequence, and the maximum alternative scenario was 9, and for one fault, which actually had the largest number of trenches, 13. And in general, we can say that what we notice is a stable number of events between the multiple history along the same fault, which means that there is a good consistency of the earthquakes record. Not too much is missing inside the trenches. And then we applied we made an advanced elaboration of the scenarios and make a selection of 12 scenarios of the 28 refined by using the ages from the further constrained data. The selection of these 12 scenarios was just only for now to to avoid overcrowding of solutions. This is an example of the scenarios for two faults, and so we have the cleared scenarios column, and then the constrained with the narrower age intervals. And also we have type column where we mark the criteria used to constrain the age interval of each event. In this case, it means a preferred portion of the intervals, and in this other case is we insert the historical and archaeological consideration. So which is the main difference between the cleared and constrained scenario at the end is the definition, basically is the definition of the most recent event and the penultimate events, for which the further constraints indication define much narrower age intervals. So by combining one of the scenarios for each fault, we obtain 4 cleared and constrained regional scenarios, but we will see later this regional analysis. So fault system, step 2. Authors suggested that based on fault geomorphic expression that some of the individual faults are part of fault system. So this means that 2 or more faults belonging to the same system may rupture simultaneously or close in time, producing a longer rupture and likely a larger magnitude event, or clustered earthquakes in time and space. So what we did to explore this possibilities, a test of 5-fault system, a test on 5-fault system based on the generated trenching record, and search for a chronological correlation of the events based on the individual fault scenarios. And what we found is that the maximum of 6 and minimum of 2 possible combination of scenarios for the fault system. So the concept is that age intervals, if age intervals overlap, both faults may have rupture within that time interval, although not necessarily at the same moment. Before I show you, to show you couple of samples, a general learning is that faults may have activated together in the past, rupturing the whole fault system, but this is not so common. I mean, not frequently. Clear data are affected by large uncertainties, so the events appear to have more potential chronological overlaps, of course. These are 2 examples. These are combination in time based on fault scenarios. And so the first example is of Indolipezza Monte Ocre fault system. In general, what we can say is that the cleared scenarios show that several events may have ruptured together, with exception for only one or maximum two events. So, so it was working well, the combination. But if we look at the constrained scenario, simultaneous ruptures occur more rarely, in particular for the recent events whose timing is better defined. A better favorable for a better case is the subequana Rocco-Perturo fault system, and scenarios suggesting suggest that the activation of the system in consecutive events in the last about 2,200 years, and so it's it would be favorable for defining a fault system. Regional scale analysis, step 3. So the combined analysis of the timing of the Palo earthquakes on fault allowed to reconstruct the time history of large earthquakes affecting the region and the landscape of the region. And so, but we wanted to explore first the data quality. And so by using the complete set of Palo events, from the scenario of all the faults built on the clear data and covering the 28 kilo-year time span, we calculated the inter-event time, which is the time elapsed between two subsequent earthquakes in the whole region. So the plot shows the overall mean and median trend in time of the inter-events with their uncertainty and for surface faulting events in the region. So what we can say is that uncertainty sharply increases starting from 5,000 BCE back in time, and since the 90% confidence interval becomes substantially larger. Combining, so we restricted our analysis, framed our analysis, regional analysis only to the past 7 kilo-year time window. And combining all the selected scenarios for the 10 faults, we can depict a total of 4 possible regional combination of fault ruptures. And this is the chronogram of one of these combinations. And in general, I can say that the rupture history reconstructs has a total of 34 and 33 events distributed on the individual faults. So the combined analysis of the timelines, of the earthquake timelines, is the basis for temporal and spatial distribution of magnitude 6 on larger earthquakes in the region. And what we did is to estimate the probability density function of inter-event times in the past 7 kilo-year. And the plot, this is a temporal plot of mean and median and 90% of the confidence bounds of inter-events. And what we can say is that behaviors of inter-events in the 4 scenarios are very similar. The values mostly are lower than 500 year, and the overall mean inter-event time are close to 230 and 240, respectively, for a clear and constrained scenario. And there is also an agreement with the average recurrence time for the region in 7 kilo-year, and also the average recurrence time tells us how frequent surface faulting events may occur on the average in the region, no matter which of the 10 fault rupture. And also a good consistency if we compare the palaeoseismological average recurrence with the historical average recurrence of the area. And particularly if we think that the time of observation, the palaeoseismological observation, is 12 times larger than that of the historical observation. And actually, the values of the recurrence becomes almost the same if we reduce the time window of the palaeoseismological time windows to 2 kilo-year. We also explored the variability of the regional earthquake recurrence, and on the basis of the 4th scenario, we attempted to identify the faults in the region that may rupture in 200-year interval, starting from today back in time. We decided 200-year time window just because we were setting this based on the regional average recurrence time. So in the figure, that is the temporal description of one of the regional rupture scenario, each colored bar represents the rupture on a specific fault. And because events age suffer uncertainties, their intersection be 200-year or multiple of these time windows, so we have longer bars. And the piling of bars mean the possibility of a concentration of surface faulting earthquakes in the region in a specific time. And this is what we call the storm, and not the simultaneous activation of multiple faults in a single earthquake. So earthquake storms are periods of recurrent damaging earthquakes. And in this case, we found that are associated with activation of a minimum of 3 faults to up to 10 distinct faults in the time interval of 200 years. Another consideration is that if we considering the 200-year regional average recurrence time and assuming regular inter-event in time, only one of the 10 faults would rupture each 200 year. Instead, as I said, we noticed the graph highlights the possibility of earthquake storms involving up to 10 faults in this period of time, so suggesting a variability in the fault's behavior in the 7 kiloyear. So finally, I show you some consideration and implications useful for the incorporation of palaeoseismological trench data in seismic hazard evaluation. And what we notice that we can say that the Palo earthquake data of these 30 years in the Apennines is adequate to be statistically elaborated and can be used for building for rupture scenarios and recognizing recurrence patterns. And the events younger than 7 kiloyear have more constraints. And of course, we have to improve the data set in the future, and can certainly derive the improvement from more data, more trenching data, but also other records from other type of unfold studies, better dating, definitely. And also we need to find alternative option in the cases of faults without available data, and also unmapped faults in the region. Thank you.
Thank you so much, Francesca. If anyone does have any quick questions, then please either say them aloud, or if you want to write them in the chat, you can. I have a quick question for you. You used a lot of examples from the central Italian Apennines, and things can vary around depending on the exact setting, but what's your sort of guide as to the minimum time between two different earthquakes that you could separate them as two separate events in a trench?
What we found, for example, in the trench in L'Aquila, 500 year was, I'll show you the slides. Which one is that? Okay, here it is. Yes, as a recurrence time, mean recurrence time of 500 years we found. That's what your question? I mean the minimum. So we could, if you have, of course, the good, let's say, stratigraphy. I mean, a regular deposition of the sediments, and if you have, of course, it depends also the recognition of the events. It depends also on the size of the slip. But what we found in this case is that even small slip, as we were talking about, even 10 centimeter or that's 30 centimeters, we still can reconstruct the history, even if they are, let's say, 500 years apart.
Okay, but less than that would be a challenge. If they were sort of only 100 or 200 years apart, it'd be very difficult.
Oh yeah, I mean, it's a challenge. That's why I was making the point of antithetic, because if we have, for example, as we saw during the Norcia earthquakes, two events very close in time, I mean, there's no way to find their signature separated in the trench, of course, even 100, even if time is a 100 year.
Thank you. Hector has a question. Hector, would you like to ask your question?
Yeah, can you hear me?
Yeah.
Yeah. Hi, Francesca. Very nice
Ciao.
talk.
Thank you.
Ciao. It's a little bit related with this same slide, but after that with the modeling that you have been doing with the data, no? It's like here you are telling us that you can see some clustering in the events, so like 500 years and then 1,000 years in between events. With all this data that you have been analyzing in your trench analysis dataset, have you seen this if you allowed like to rupture 3-4 faults in the same event, that this is preventing, or this is like provoking that the time span between events it's larger, so it's like a clustering, and then you have a more time in between, and then you have maybe some more I don't know, space events or whatever. It's like, since you have this large amount of data, you can see this clustering. It's like
I don't know if you are referring. I'm not sure if I answered to you in the correct way.
Francesca, it's the let's say when you are involving more than one fault in a large event, it's like you are just releasing a lot of moment on the fault, a lot of energy, so you will have more time to the next one. So maybe this could be related to a larger time in between events, and then
no, we don't. Yeah, no, okay. No, we do not. I mean, we should look at the data in this with this intention. Yeah.
Okay, thank you.
Thank you, Hector. There's a question from Maria in the chat, which asks, is it common to find secondary ruptures associated to different primary faults, or do you think that a secondary fault always belongs to a particular primary fault? So when you see secondary ruptures, is it always associated with the same fault, or could they be from more than one fault?
So the question is, it's in the chat, so I can't read.
So I can also try to can you hear me?
Yes.
Okay. Congratulations for the talk, Francesca. It was great. Since you've seen many cases, I was wondering, when you see in the field a secondary rupture, or what you think it's a secondary rupture, have you ever associated that secondary behavior to more than one primary fault? That means I always ask if when you see a secondary rupture, this small fault can rupture like together with different primary faults.
Okay, no, sorry, Maria. Yes, now okay, I think that the difference between primary and secondary faults, I think that in the next talk, Paolo Boncio will explain and illustrate much better. But what I was talking about with the antithetic, for example, I call the antithetic secondary, but to me, that fault goes and join at greater depth the main fault plane, of course. So I think that in this case, the antithetic will move always, let's say, associated to the main, the principal fault, and there is no reason why. I mean, I don't see it. Maybe can be triggered as a sympathetic with another, with an earthquake along a different and nearby fault, but still, I think that it's associated to the main activation. And then regarding instead the secondary faults, for example, when we have a wide distribution, I think that, yes, I think that they move always associated to the same fault, because they are when I talk about secondary fault, I talk about faults that join the fault plane at depth. But they're just secondary because they have minor displacement.
Okay, they merge on that. Okay, thank you.
Thank you, Maria, and thank you again, Francesca, for today. We look forward next time, as Francesca has mentioned, Paolo Boncio will be speaking at our usual time of the second Monday of the month at 3 p.m. for Central European time on Monday, the 8th of March. So Paolo Boncio. So if you want to hear about fault displacement hazard, a geological perspective, do join us on the 8th of March at 3 p.m. Central European time. And then in April, we're going to be hearing from Ross Stein on Coulomb stress transfer. So that's the next 2 sessions in our series. Thank you for all of those of you who joined today, and we look forward to seeing you again next time.
Ciao a tutti.